Space contains the most powerful magnifying glasses in existence. Right now, invisible forces are bending starlight from the edge of the universe. This cosmic magnification happens without any mirrors or lenses. Gravity alone creates these impossible optical effects. Tonight, we're following light on its strangest possible journey. We'll discover why the universe's heaviest objects become its best telescopes. Before we explore these cosmic lenses, drop a comment about what you think could bend light in space. If you enjoy these universe deep dives, consider subscribing. These cosmic discoveries are meant to be shared. Astronomers kept finding impossible photographs, perfect circles of light floating in completely empty space. These weren't planets or stars. They were something much stranger. The circles turned out to be entire galaxies. But galaxies aren't supposed to look like rings. They're supposed to look like spiral disks or fuzzy blobs. Something was warping the light from these distant galaxies, twisting their normal appearance into perfect geometric shapes. The effect only happened when conditions lined up exactly right. Scientists call these warped images Einstein rings, named after the physicist who predicted them. They form when a massive galaxy sits directly between us and a much more distant galaxy behind it. The foreground galaxy acts like a cosmic magnifying glass, bending the background galaxy's light into a complete circle around itself. This perfect alignment happens incredibly rarely. But when it works, we get to see galaxies that would otherwise be completely invisible to us. Here's something that breaks common sense completely. Gravity doesn't just pull objects toward each other. It actually bends the empty space around massive objects. This means space isn't flat like most people imagine. Near heavy objects, space curves like a stretched rubber sheet with a bowling ball sitting on it. Everything traveling through that curved space follows the bends and warps. Light gets caught in this geometric distortion too. Even though light particles have no weight, they still follow the curved paths that gravity creates in space. Galaxy groups that contain thousands of individual galaxies create serious warping effects. These galaxy clusters weigh more than 1 billion suns combined. That's enough mass to noticeably bend light rays passing nearby. Astronomers can measure these light-bending effects with their telescopes. Each massive galaxy cluster becomes a natural lens that magnifies whatever lies behind it. The universe builds its own optical instruments using nothing but gravity and curved space. The universe's gravity-powered telescopes make human technology look like toy magnifying glasses. These cosmic lenses can magnify distant objects by factors that engineers can only dream about. The largest telescopes on Earth struggle to see galaxies beyond a certain distance. The light becomes too faint and spread out to detect. But gravity lenses collect and focus that same light, making invisible objects suddenly bright enough to study. Some gravitational lenses boost an object's brightness by more than 100 times. That's like turning a dim candle into a powerful searchlight. Objects that should be completely undetectable become easily visible. The magnification happens automatically across the entire electromagnetic spectrum. Radio waves, visible light, X-rays, everything gets focused equally well. Human telescopes need different instruments for different types of light. Gravity lenses handle them all simultaneously. These natural telescopes never need maintenance, never break down, and never run out of power. They've been operating perfectly for billions of years, waiting for astronomers to figure out how to use them. Gravitational lenses create the ultimate cosmic magic trick. They can make one distant galaxy appear as 2, 3, or even 4 separate objects. in the same photograph. Each image shows the exact same galaxy from slightly different angles. The effect happens when light from a background object takes multiple paths around a foreground mass. Some light rays curve around the left side, others around the right side. Each group of rays reaches Earth at different times and from different directions. Astronomers see what looks like several different galaxies arranged around a central massive object. But detailed analysis reveals they're all images of the same galaxy behind the lens. The multiple copies often have different brightness levels and slight shape distortions. The most extreme cases produce 4 separate images arranged in a cross pattern around the lensing galaxy. This configuration gets called an Einstein cross, another tribute to the scientists who first described how gravity could bend light. These multiple images provide a powerful tool for measuring cosmic distances. By comparing the brightness and timing of each image, astronomers can calculate exactly how far away both the lens and the background object are located. Gravitational lensing doesn't just bend light, it concentrates it. This focusing effect acts like a cosmic amplifier, making distant objects appear much brighter than they actually are. The brightness increase can be dramatic. Objects that would normally be too faint to detect become easily visible through gravitational magnification. It's like having a natural spotlight suddenly illuminate something in a dark room. The amplification factor varies depending on the lens geometry. Objects passing directly behind the most massive parts of a galaxy cluster receive the strongest boost. Some get magnified by factors of 10, 50, or even more. This natural amplification system lets astronomers study objects they could never observe otherwise. Distant galaxies that formed when the universe was very young become bright enough to analyze in detail. Stars in nearby galaxies that would normally be invisible suddenly stand out clearly. The focusing effect preserves all the scientific information in the light. Astronomers can study the chemistry, temperature, and motion of amplified objects just as accurately as if they were using a more powerful telescope. Nature provides the magnification for free. Light from gravitationally lensed objects doesn't all arrive at the same time. Different paths around the lensing mass have different lengths and experience different amounts of gravitational time delay. This creates a cosmic time machine effect. When a distant object flickers or changes brightness, astronomers see those changes happen multiple times in the different lensed images. The same event replays with delays of days, months, or even years between the repeated appearances. The time delays happen because light traveling closer to massive objects experiences stronger gravitational effects. Time itself runs slower in strong gravitational fields, causing light to lose time during its journey. Different paths around the lens experience different amounts of this time stretching. Astronomers use these time delays as precision measuring tools. By timing how long light takes to travel each path, they can calculate the exact mass of the lensing object and the distances to both the lens and the background source. The time delay effect also provides multiple opportunities to study brief cosmic events. If a distant star explodes as a supernova behind a gravitational lens, astronomers might get to watch the explosion happen several times as the delayed light from different paths arrives at Earth. Gravitational lensing exposes matter that can't be seen any other way. Most of the mass in galaxy clusters consists of invisible dark matter that doesn't emit or absorb light. But this hidden matter still bends light rays passing through the cluster. Astronomers can map the dark matter distribution by measuring how background galaxies get distorted. the invisible mass reveals itself through the warping patterns it creates in more distant light sources. The technique works like detective work with cosmic fingerprints. Each type of mass distribution creates characteristic distortion patterns. By analyzing thousands of background galaxy shapes, astronomers can reconstruct the invisible matter map. The results show that visible stars and gas make up only a small fraction of galaxy cluster mass. The majority consists of dark matter arranged in vast invisible structures that dwarf the visible galaxies floating within them. These dark matter maps provide crucial clues about how the universe evolved. The invisible structures formed first, then attracted normal matter to create the galaxies and stars we can see. Gravitational lensing gives us X-ray vision into the universe's hidden architecture. Gravitational lensing provides one of the most accurate methods for measuring cosmic distances. The lens effect depends on the precise geometry between the observer, the lens, and the background object. This geometry acts like a cosmic ruler stretching across space. The measurement technique uses the time delays between multiple images of the same lensed object. The delays depend on both the lens mass and the distances involved. By measuring the time differences accurately, astronomers can solve for the distances. This method gives independent confirmation of cosmic distance measurements made by other techniques. When different methods agree, astronomers gain confidence in their understanding of the universe's size and expansion rate. The distance measurements help determine fundamental cosmic properties. How fast is the universe expanding? How much dark energy exists? How old is the universe? Gravitational lensing provides precise data for answering these basic questions. The technique works best for measuring very large distances that stretch halfway across the observable universe. These measurements help astronomers understand what the universe was like when it was much younger than it is today. Gravitational magnification allows astronomers to see further back in time than any conventional telescope could manage. The natural amplification brings the universe's first galaxies within range of detailed study. These ancient galaxies formed when the universe was less than 1 billion years old. They represent the cosmic dawn, when the first major star formation was just beginning. Without gravitational magnification, they would remain forever invisible. The lenses reveal galaxies that are smaller, more irregular, and actively forming stars at incredible rates. These early systems look completely different from the mature spiral and elliptical galaxies we see in the nearby universe. The observations provide direct evidence for how cosmic structure evolved over time. Astronomers can trace the transformation from small, chaotic early galaxies to the organized systems that exist today. This cosmic archaeology helps answer fundamental questions about galaxy formation. When did the first galaxies appear? How quickly did they grow? What triggered the initial burst of star formation that lit up the early universe? Gravitational lensing can detect planets orbiting stars thousands of light years away. When a star with planets passes in front of a more distant background star, the gravitational field of the planetary system creates detectable distortions in the lensing effect. The technique works by monitoring background stars for temporary brightness increases caused by foreground objects acting as gravitational lenses. Most events show the smooth brightening pattern of a single star acting as a lens. But when the foreground star has planets, the smooth pattern gets interrupted by additional spikes or dips in brightness. Each planet creates its own small lensing effect that modifies the overall light curve in characteristic ways. The method can detect planets at much greater distances than other planet hunting techniques. It's sensitive to planets with a wide range of masses and orbital distances, including Earth-sized worlds in the habitable zones around their stars. Microlensing surveys have discovered dozens of exoplanets using this technique. The method provides unique information about planet populations in different parts of our galaxy, helping astronomers understand how common planetary systems really are. Gravitational lensing serves as a cosmic mapping tool that reveals how matter is distributed throughout the universe. By measuring tiny distortions in millions of background galaxies, astronomers can chart the locations of both visible and invisible matter. The technique works like creating a topographic map of cosmic mass. Dense regions containing galaxy clusters show up as peaks, while empty voids appear as valleys. The resulting maps show the universe's web-like structure of filaments and cavities. These cosmic surveys cover enormous volumes of space, mapping regions that contain millions of galaxies. The statistical analysis of galaxy shapes reveals subtle lensing effects would be impossible to detect in individual objects. The maps provide crucial tests of theories about how cosmic structure formed and evolved. Computer simulations of universe evolution can be compared directly with the observed mass distribution to see if the models match reality. The large-scale structure maps also help measure the properties of dark energy, the mysterious force that's causing the universe's expansion to accelerate. By tracking how structure growth has changed over cosmic time, astronomers can constrain the nature of this enigmatic component. Einstein couldn't accept the old explanation for gravity. Newton said massive objects pulled on each other across empty space. But how could objects influence each other without touching? What invisible force reached across the void? The answer demolished everything scientists thought they knew about space and time. Mass doesn't pull on objects. It warps the geometry of space and time itself. Everything moving through that warped region follows the curved paths that mass creates. This theory is called general relativity. It describes gravity not as a force, but as curved spacetime. Heavy objects create deep curves in space and time. Light objects create shallow curves. Every object with mass reshapes the universe around itself. Stars, planets, and galaxies all bend spacetime. The more massive the object, the deeper the curves it creates. These curves guide the motion of everything passing nearby, including particles of light. Space and time become a flexible fabric that responds to the presence of matter and energy. You cannot tell the difference between gravity and acceleration. This sounds impossible, but it's the foundation of Einstein's entire theory. The effects feel identical because they actually are identical. Imagine you're in an elevator with no windows. Someone accelerates the elevator upward. You feel pressed against the floor. Now imagine the same elevator sitting still on Earth's surface. Gravity pulls you toward the floor with exactly the same feeling. Einstein realized these two situations are fundamentally the same thing. What we call gravity is just the experience of moving through curved spacetime. There's no difference between gravitational acceleration and mechanical acceleration. This insight is called the equivalence principle. It means that gravity isn't a force at all. It's the natural result of spacetime curvature. Objects in freefall are actually following the straightest possible paths through curved space. The principle explains why gravitational lensing works. Light follows the geometry of spacetime just like everything else. When spacetime curves, light curves with it. Light cannot choose its own path. It must follow the geometry that massive objects create in spacetime. These paths are called geodesics, the shortest possible routes through curved space. On flat surfaces, the shortest distance between 2 points is a straight line. But space near massive objects isn't flat. It's curved and twisted by gravity. In curved space, the shortest path looks bent to outside observers. Think of an airplane flying from New York to Tokyo. The shortest route goes over the North Pole, not in a straight line across the Pacific. The curved surface of Earth makes polar routes shorter, even though they look longer on flat maps. Light works the same way in curved spacetime. Photons always take geodesic paths, the routes that minimize travel time through warp space. Near massive objects, these geodesics curve dramatically. This geodesic motion explains every gravitational lensing effect we observe. Light isn't being pulled or deflected by gravity. It's simply following the straightest available path through space that massive objects have curved. Scientists needed precise equations to calculate how mass curves spacetime. The math behind Einstein's theory is incredibly complex. But one solution stands out for its elegance and usefulness. Carl Schwarzschild solved Einstein's equations for the simplest possible case. How does spacetime curve around a single, perfectly spherical mass? His solution describes the warping pattern around stars, planets, and black holes. The Schwarzschild solution shows exactly how space and time bend near any round, massive object. The warping gets stronger closer to the object's center. It gets weaker with distance, but never completely disappears. This mathematical description lets astronomers calculate gravitational lensing effects precisely. They can predict how much any massive object will bend light passing at any distance. The equations work for everything from planets to galaxy clusters. The solution reveals that massive objects create what looks like wells or valleys in spacetime. The deeper the well, the stronger the gravitational effects become. Einstein's theory makes testable predictions. It provides exact formulas for calculating how much massive objects will deflect light passing nearby. The math works for any mass at any distance. The deflection angle depends on two main factors. How massive is the lensing object? How close does the light pass to that object? More mass creates stronger bending. Closer approaches create sharper deflections. The formula shows that light passing just at the sun's surface gets bent by about 1.75 arcseconds. That's less than 1/1000th of a degree, but it's measurable with precise instruments. For more massive objects, like galaxy clusters, the deflection becomes much larger. Light can bend by several arcminutes, angles visible in ordinary photographs. The strongest lenses bend light by complete circles, creating Einstein rings. These calculations let astronomers use gravitational lenses as precision tools. They can measure masses, distances, and the expansion rate of the universe using light deflection measurements. Light always chooses the path that takes minimum time to travel. This principle, discovered by Pierre de Fermat, explains many optical phenomena. It also explains how gravitational lensing works. In flat spacetime, the fastest route between 2 points is a straight line. But massive objects slow down time itself near their surfaces. Clocks run slower in stronger gravitational fields. This creates a cosmic traffic problem for light. Taking a straight path means traveling through regions where time runs slow. Taking a curved detour around the mass leads through regions where time runs faster. Light solves this problem by finding the perfect compromise route. It bends just enough to avoid the slowest time regions while not detouring too far. The result is the curved paths we observe in gravitational lensing. Fermat's principle shows that light deflection is really about time, not space. Light bends to minimize its travel time through the complex time variations that gravity creates around massive objects. Scientists use a simple model to help people visualize curved spacetime. Imagine space as a stretched rubber sheet. Massive objects sit on this sheet like bowling balls, creating depressions and warps. Small objects rolling across this warped sheet follow curved paths around the depressions. The deeper the depression, the more dramatically objects curve. This models how gravity works in the real universe. The rubber sheet analogy has limitations, but it captures the essential idea. Mass creates geometric curvature. This curvature guides the motion of everything passing through the region, including light. Galaxy clusters create the deepest gravitational wells in the universe. These cosmic valleys can trap and focus light from much more distant sources. The focusing effect creates the magnification we observe in gravitational lensing. Understanding spacetime curvature as landscape helps explain why some regions produce stronger lensing effects than others. The deepest gravitational wells become the most powerful natural telescopes. Here's something that seems impossible. Light particles have no mass whatsoever, yet they still respond to gravitational effects. How can massless particles be influenced by gravity? The answer reveals the true nature of gravity. Gravity doesn't pull on mass. It curves the geometry that everything must travel through. Even massless particles must follow the paths available in curved spacetime. Photons always travel at the speed of light along geodesic paths. In flat spacetime, geodesics are straight lines. In curved spacetime near massive objects, geodesics become curved paths that bend around the mass. The photons aren't being pulled or pushed by gravitational force. They're simply following the only paths available in the curved spacetime geometry. Mass creates the curves. Light follows them automatically. This explains why gravitational lensing affects all types of electromagnetic radiation equally. Radio waves, visible light, and X-rays all follow the same curved paths through warped spacetime around massive objects. Einstein's theory seems completely different from Newton's classical physics. But in weak gravitational fields, the two theories give nearly identical predictions. Einstein's theory contains Newton's theory as a special case. When gravitational fields are weak and velocities are slow compared to light speed, spacetime curvature becomes very shallow. In this limit, curved spacetime behaves almost exactly like flat space with gravitational forces. Most everyday gravitational effects fall into this classical regime. Planets orbiting the Sun, objects falling near Earth's surface, and even light bending around the Sun show only small deviations from Newton's predictions. The differences become important only in extreme situations. Very massive objects, very strong gravitational fields, or very high speeds reveal where Einstein's theory diverges from classical physics. This gradual transition between theories gives scientists confidence in Einstein's framework. It explains all the phenomena that Newton's theory handled correctly, plus many new effects that classical physics couldn't predict. Einstein's theory made a stunning prediction that seemed impossible to test. During a solar eclipse, starlight passing near the Sun should bend by a measurable amount. The stars should appear shifted from their normal positions. Arthur Eddington organized expeditions to observe the total solar eclipse of 1919. His teams photographed stars near the eclipsed Sun and compared their positions to photographs taken when the Sun was elsewhere in the sky. The measurements confirmed Einstein's prediction with remarkable accuracy. Stars appeared shifted by exactly the amount Einstein's equations predicted. Light really was being bent by the sun's gravity. This observation instantly made Einstein famous worldwide. It provided the first direct proof that massive objects curve spacetime and deflect light. Gravitational lensing changed from theory to observed fact. Modern observations have confirmed light deflection effects with extraordinary precision. Radio telescopes can measure deflections thousands of times smaller than Eddington detected, verifying Einstein's theory to incredible accuracy. Astronomers keep finding the same galaxy in multiple places within single photographs. The identical object appears 2, 3, or even 4 times in the same image. Each copy shows exactly the same galaxy from slightly different angles. This cosmic duplication happens when light from a distant galaxy takes several different routes around a massive foreground object. Some photons curve around the left side of the intervening mass. Others bend around the right side. Each group of light rays reaches Earth from different directions. The effect is called multiple imaging, and it creates the strangest optical illusions in the universe. What looks like several separate galaxies arranged in a pattern is actually one galaxy whose light has been split and redirected along different paths. The multiple images often have different brightness levels and shapes. Light taking longer routes arrives dimmed and stretched. Light following shorter paths stays brighter and less distorted. But detailed analysis always reveals they show the same original object. Each massive galaxy cluster becomes a cosmic funhouse mirror that creates multiple reflections of whatever lies behind it. Every gravitational lens has a characteristic size that determines how its effects appear. When a background object sits at exactly the right distance and alignment, it forms a perfect ring around the foreground mass. The size of this ring follows precise rules. Scientists call this measurement the Einstein radius. It depends on the mass of the lensing object and the distances involved. Heavier lenses create larger rings. Objects at optimal distances produce the most dramatic effects. For typical galaxy clusters, Einstein rings measure several arcseconds across. That's large enough to see clearly in detailed telescope photographs. The rings maintain perfect circular symmetry when the alignment stays exact. The Einstein radius acts like a cosmic ruler for measuring lens properties. By measuring the ring size, astronomers can calculate the exact mass of the lensing galaxy or cluster. The geometry provides a direct mass measurement tool. This characteristic size explains why some gravitational lenses produce dramatic effects while others show subtle distortions. The Einstein radius sets the scale for all lensing phenomena. Certain locations behind gravitational lenses produce unlimited magnification. Objects positioned at these special points become infinitely bright in theory. In practice, they shine far brighter than should be possible. These extreme magnification regions form complex curved patterns called caustic lines. The name comes from optics, where similar focusing effects create bright curves of light. Cosmic caustics work the same way but on enormous scales. When a background object crosses one of these caustic lines, its brightness jumps dramatically. Stars that would normally be invisible suddenly become easily detectable. Galaxies that appear faint elsewhere blaze like cosmic beacons. The caustic patterns depend on the exact mass distribution of the lensing object. Single galaxy lenses create simple caustic curves. Galaxy clusters produce complicated networks of caustic lines that intersect and branch. Understanding caustic geometry helps astronomers predict where the strongest magnification effects will occur. These become prime hunting grounds for detecting extremely distant objects. Gravitational lenses have invisible boundary lines where their effects change dramatically. Cross one of these boundaries and moderate magnification suddenly becomes extreme amplification. Scientists map these boundaries to understand how lenses work. The boundary lines are called critical curves. They mark the borders between different magnification regions in space. Inside the critical curves, magnification stays reasonable. Right at the boundaries, magnification approaches infinite values. Critical curves form closed loops around massive lensing objects. Simple lenses create single circular critical curves. Complex lenses like galaxy clusters produce multiple critical curves with complicated shapes that can intersect and merge. Objects positioned exactly on critical curves experience the strongest possible magnification effects. Their light gets focused so intensely that they appear much brighter than they actually are. This extreme focusing reveals objects that would otherwise remain invisible. Mapping critical curves requires careful analysis of multiple background objects. Each lensed image provides clues about where the boundaries lie. The complete map reveals the gravitational landscape of the lensing mass. Background galaxies near massive clusters undergo extreme shape distortion. Round spiral galaxies stretch into long, thin arcs that span enormous distances across the sky. These giant arcs rank among the most spectacular sights in astronomy. The stretching happens because different parts of the background galaxy experience different magnification strengths. The galaxy's center might get magnified 10 times, while its edges get magnified 50 times. This differential stretching pulls the galaxy into an arc shape. Giant arcs can stretch across several arcminutes of sky. That's large enough to see easily in telescope images. The most extreme cases create nearly complete semicircles of stretched galaxy light around the central cluster. The arc shapes preserve all the scientific information about the original galaxy. Astronomers can study the chemistry, star formation, and structure of these distant objects despite their dramatic distortion. The stretching acts like a natural zoom lens. These giant arcs provide natural laboratories for studying galaxy evolution. Many of the stretched galaxies formed when the universe was much younger. The gravitational magnification brings their ancient light within range of detailed analysis. Gravitational lenses don't just bend light. They collect and concentrate it. This focusing effect can boost an object's apparent brightness by factors that range from modest to extreme. The amplification depends entirely on geometric alignment. Scientists measure this effect using amplification factors. A factor of 10 means the object appears 10 times brighter than normal. A factor of 100 brightness increases that transform invisible objects into easily detectable ones. The strongest amplification occurs near critical curves and caustic lines. Objects in these special locations can appear hundreds of times brighter than they actually are. Some theoretical predictions suggest amplification factors could reach thousands. This natural amplification system lets astronomers study objects they could never observe with conventional telescopes. Distant galaxies that would normally be too faint become bright enough for detailed spectroscopic analysis. Individual stars in nearby galaxies suddenly stand out clearly. The amplification preserves all wavelengths of light equally. Radio waves, visible light, and X-rays all get boosted by the same factors. This creates opportunities for multi-wavelength studies of amplified objects. A strange mathematical law controls gravitational lensing. The total number of images always follows specific rules based on the geometry involved. You can't have just any random number of images. The rule is called parity conservation. It requires that gravitational lenses produce either an odd number of images or an even number, depending on the source position. The images alternate between different brightness patterns in predictable ways. Most gravitational lenses create either 2 images or 4 images of background objects. 3-image systems occur rarely and only under special geometric conditions. 5 or more images require extremely complex mass distributions. This mathematical constraint helps astronomers identify gravitational lensing effects. When they find multiple images that follow the parity rules, they know they're looking at lensed objects rather than separate galaxies that happen to look similar. The parity conservation rule also guides searches for new lensing systems. Computer algorithms can scan telescope surveys for image patterns that match the expected mathematical relationships. Gravitational lenses scramble the positions of background objects. What astronomers observe are distorted images shifted from their true locations. Scientists need mathematical tools to work backwards from observations to reality. The process uses something called the lens equation. This mathematical relationship connects the observed image positions to the actual source positions and the mass distribution of the lens. Solving the equation reveals where objects really sit in space. The calculation becomes complex for realistic lenses with irregular mass distributions. Astronomers use computer modeling to solve the lens equations numerically. The models must account for every detail of the lensing mass structure. Successful lens modeling produces a complete map of the gravitational field. This map shows not just where the lensed objects are located, but also how mass is distributed throughout the lensing system. The lens equation serves as a cosmic GPS system. It helps astronomers navigate the distorted view of space that gravitational lenses create, revealing the true arrangement of objects behind the lens. Gravitational lensing provides the most accurate method for weighing massive objects in space. The distortion patterns reveal exactly how much mass is present and where it's located. This cosmic scale works for individual galaxies and entire galaxy clusters. The technique analyzes the positions and shapes of multiple lensed images. Each image provides information about the gravitational field strength at different locations. Combining many measurements creates a detailed mass map. The mass measurements include all matter present, both visible stars and invisible dark matter. Most galaxy clusters contain 5 times more dark matter than normal matter. Gravitational lensing reveals the complete picture. Mass measurements from gravitational lensing agree remarkably well with other techniques. When different methods produce similar results, astronomers gain confidence in their understanding of cosmic mass distributions. The precision of lens-based mass measurements continues improving as telescope technology advances. Modern surveys can map mass distributions with unprecedented detail and accuracy. Strong gravitational lenses create natural time machines for astronomy. The extreme magnification brings galaxies from the early universe within range of detailed study. These ancient systems formed when cosmic conditions were completely different. The magnified galaxies show what star formation looked like billions of years ago. They appear smaller, more irregular, and much more actively forming stars than modern galaxies. The early universe was a more chaotic and energetic place. High redshift measurements confirm these galaxies' ancient ages. The term redshift describes how light from distant objects gets stretched to longer, redder wavelengths by cosmic expansion. Higher redshift means greater distance and earlier cosmic time. Some lensed galaxies formed less than 1 billion years after the Big Bang. They represent the cosmic dawn. when the first major burst of star formation was lighting up the universe. Without gravitational magnification, these objects would remain forever undetectable. These observations provide direct evidence for how cosmic structure evolved over time. Astronomers can trace the transformation from chaotic early galaxies to the organized spiral and elliptical systems we see today. The most powerful gravitational lenses aren't single galaxies. They're entire clusters containing hundreds or thousands of galaxies grouped together. These cluster lenses create the most complex and spectacular lensing effects in the universe. Galaxy clusters represent the largest gravitationally bound structures in the cosmos. They contain enormous amounts of both visible matter and dark matter concentrated in relatively small regions. This mass concentration creates extreme spacetime curvature. Cluster lenses produce multiple Einstein rings, giant arcs, and numerous multiply-imaged background objects all in the same field of view. The overlapping effects from different cluster galaxies create incredibly complex distortion patterns. The most massive clusters can magnify background objects by factors of 50 or more. This extreme amplification reveals populations of distant galaxies that no conventional telescope could detect. Cluster lenses extend our cosmic horizon significantly. Understanding cluster lenses requires sophisticated computer modeling. The gravitational effects from hundreds of individual galaxies must be calculated simultaneously to predict the observed lensing patterns accurately. Even within the strongest gravitational lenses, smaller mass concentrations create subtle additional effects. These substructures produce tiny distortions that require careful analysis to detect. Finding them reveals hidden components of cosmic architecture. The substructures include individual galaxies within clusters, dark matter subhalos, and other mass concentrations too small to see directly. Each creates its own weak gravitational field that adds small perturbations to the main lensing effects. Detecting substructure requires comparing observations to theoretical models. Computer simulations predict what lensing patterns should look like for smooth mass distributions. Deviations from these smooth models reveal the presence of substructure. The technique works like cosmic archaeology by measuring tiny anomalies in lensed image positions and shapes. Astronomers can infer the properties of mass concentrations that can't be observed any other way. Substructure detection helps test theories of cosmic structure formation. The number and properties of small-scale mass concentrations provide crucial constraints on models of how the universe evolved from smooth initial conditions to today's complex structure. Most gravitational lensing effects are too weak to see in individual galaxies. The distortions are tiny, much smaller than the dramatic rings and arcs that strong lenses create. But when astronomers analyze thousands of galaxy shapes together, subtle patterns emerge. This weak distortion effect is called cosmic shear. The term describes how large-scale cosmic structures slightly stretch and twist the shapes of distant galaxies behind them. Each individual galaxy shows only microscopic changes, but statistical analysis reveals the underlying pattern. The shear signal works like a cosmic fingerprint. Different mass distributions create different shearing patterns. By measuring how galaxy shapes correlate across large regions of sky, astronomers can map the invisible matter responsible for the distortions. Cosmic shear operates on enormous scales. The lensing structures can stretch across hundreds of millions of light years. The background galaxies being distorted lie billions of light years behind these massive foreground systems. This technique transforms millions of faint galaxy images into a powerful tool for mapping dark matter throughout the universe. Galaxies come in many different shapes naturally. Some appear perfectly round, others look stretched or oval-shaped. Astronomers need to separate natural galaxy shapes from distortions caused by gravitational lensing effects. Scientists measure something called ellipticity to quantify galaxy shapes. This number describes how much a galaxy deviates from perfect circular symmetry. Round galaxies have ellipticity near zero. Stretched galaxies have higher ellipticity values. The measurement process requires extreme precision. Weak lensing changes ellipticity by less than 1% in most cases. Detecting such tiny shape changes demands sophisticated image analysis techniques and enormous galaxy samples. Random galaxy orientations would cancel out if no lensing occurred, but gravitational shear creates preferred alignment directions that show up in statistical analysis. Thousands of galaxies must align slightly in the same direction for the signal to emerge above noise. Modern surveys measure ellipticity for millions of galaxies simultaneously. This massive statistical approach reveals weak lensing signals that would be completely invisible in smaller samples. Not all galaxy alignment patterns come from gravitational lensing. Galaxies can naturally align with each other due to the cosmic environment where they formed. Scientists must carefully separate these intrinsic alignments from lensing effects. Intrinsic alignment happens when galaxies form within the same large-scale cosmic structures. The gravitational tidal forces that shape galaxy formation can create preferred orientations. Nearby galaxies often point in similar directions for this reason. This natural alignment effect contaminates weak lensing measurements. If astronomers don't account for intrinsic alignments, they might mistake natural galaxy orientations for gravitational distortion signals. The contamination can completely overwhelm genuine lensing effects. Separating intrinsic alignment from lensing requires careful analysis of galaxy distances and environments. Lensing affects background galaxies at different distances than the structures causing the distortion. Intrinsic alignment affects galaxies within the same structures. Advanced statistical techniques can distinguish between these two effects. By analyzing how alignment patterns change with galaxy distance and local density, astronomers can isolate pure gravitational lensing signals. Weak lensing analysis produces detailed maps of where mass concentrates throughout space. These maps don't show individual galaxies or stars. They reveal the total matter distribution, including invisible dark matter that can't be observed directly. The mapping technique creates what scientists call convergence maps. Convergence measures how much total mass lies along each line of sight through space. Higher convergence indicates more matter. Lower convergence shows regions with less mass concentration. Creating convergence maps requires sophisticated mathematical analysis. Astronomers must integrate all the matter lying between Earth and distant background galaxies. The calculation accounts for different distances and the varying strength of lensing effects. The resulting maps look like cosmic topographic charts. Dense regions containing galaxy clusters appear as peaks. Empty cosmic voids show up as valleys. The overall pattern reveals the universe's largest structures. These mass maps provide independent confirmation of cosmic structures seen through other methods. When different techniques produce similar maps, astronomers gain confidence in their understanding of how matter is distributed throughout space. Weak lensing shear signals contain two fundamentally different types of distortion patterns. Understanding this difference requires mathematical analysis that decomposes the total shear into separate components with distinct physical meanings. Scientists call these components E modes and B modes, borrowing terminology from electromagnetic field theory. E-mode shear has no rotational component. The distortions point radially outward from mass concentrations. B-mode shear has rotational patterns that curl around in space. Gravitational lensing by normal mass distributions produces only E-mode shear patterns. The gravitational forces point toward mass concentrations, creating radial distortion patterns. B-mode signals shouldn't exist if standard physics correctly describes gravitational lensing. Detecting B-mode shear would indicate something unusual is happening. Possible sources include systematic measurement errors, exotic physics, or unknown types of cosmic structures. Most B-mode detections so far trace back to measurement problems rather than new physics. The E-mode and B-mode decomposition provides a powerful consistency check for weak lensing analysis. Clean E-mode signals with minimal B-mode contamination indicate reliable measurements and standard gravitational physics. Individual galaxies create their own small gravitational lensing effects. These localized distortions affect nearby background galaxies within a few arcnauts of each foreground galaxy. The effect is much weaker than cluster lensing but detectable with precise measurements. This phenomenon is called galaxy-galaxy lensing. It measures the average shear pattern around large samples of foreground galaxies. No single galaxy produces detectable distortion, but statistical analysis of thousands reveals the signal. The technique works by selecting foreground galaxies at known distances and measuring the average shape distortion of background galaxies surrounding each foreground object. The background galaxies must lie significantly further away to experience lensing. Galaxy-galaxy lensing probes the dark matter halos that surround individual galaxies. Most galaxies sit within invisible dark matter structures that extend far beyond their visible boundaries. The lensing signal reveals these hidden halos directly. Measurements show that typical spiral galaxies are surrounded by dark matter halos extending several 100,000 light-years from their centers. The total halo mass often exceeds the visible galaxy mass by factors of 10 or more. Galaxy clusters produce the strongest weak lensing signals in the universe. The intense gravitational fields around these massive structures create easily detectable shear patterns in background galaxy populations extending far from cluster centers. Cluster lensing analysis maps how dark matter is distributed throughout these cosmic giants. The measurements reveal dark matter halos that extend millions of light-years from cluster cores. These invisible structures contain most of the cluster mass. The lensing strength decreases with distance from cluster centers following predictable patterns. By measuring how the shear signal varies across different distances, astronomers can determine the total cluster mass and its radial distribution. Cluster lensing provides independent mass measurements that can be compared with other techniques. X-ray observations reveal hot gas trapped within cluster gravitational wells. Galaxy motions indicate the gravitational field strength. All methods should give consistent results. The comparison between different mass measurement techniques has revealed important physics. In some colliding clusters, the dark matter and normal matter have separated spatially. This separation provides strong evidence for dark matter's existence as a distinct component of cosmic structure. Weak lensing analysis requires precise knowledge of galaxy distances. Astronomers must know which galaxies serve as lenses and which serve as background sources. This distance information determines the expected lensing strength and geometry. Scientists use a technique called photometric redshift estimation to measure galaxy distances. The method analyzes galaxy colors in different wavelength bands. More distant galaxies appear redder due to cosmic expansions stretching their light to longer wavelengths. Photometric redshift works by comparing observed galaxy colors to models of how galaxy spectra change with distance. Computer algorithms match the observed colors to predicted color patterns, yielding distance estimates for millions of galaxies simultaneously. The technique provides distance estimates accurate to about 10% for most galaxies. This precision suffices for statistical weak lensing analysis, though it's less accurate than spectroscopic redshift measurements that require much more observing time. Accurate photometric redshifts are crucial for weak lensing cosmology. Incorrect distance estimates would lead to wrong conclusions about cosmic structure, dark matter properties, and the universe's expansion history. Weak lensing shear correlations across different angular scales reveal how cosmic structure has evolved over billions of years. This statistical analysis connects current observations to the universe's expansion and structure formation history. The analysis measures something called the shear power spectrum. This describes how strongly galaxy shapes correlate as a function of their angular separation on the sky. Small-scale correlations probe dense cosmic structures. Large-scale correlations reveal broader patterns. The power spectrum shape depends on fundamental cosmic parameters like dark matter density, dark energy strength, and the universe's expansion rate. Different parameter combinations produce different correlation patterns that can be distinguished observationally. By comparing observed power spectra to theoretical predictions, astronomers can measure these cosmic parameters precisely. The technique provides independent confirmation of results from other methods like cosmic microwave background analysis and supernova studies. The measurements track how cosmic structure has grown over time as the universe expanded and dark energy began dominating cosmic dynamics. This growth history provides crucial tests of our understanding of cosmic evolution. Weak lensing measurements are extremely challenging because the signals are so small. Many systematic effects can mimic or contaminate a genuine lensing signals. Controlling these systematics requires careful attention to telescope optics, image analysis, and statistical methods. One major source of systematic error is called point spread function contamination. Atmospheric turbulence and telescope optics blur star and galaxy images in ways that can mimic gravitational shear. If this blurring isn't corrected perfectly, it creates false lensing signals. Selection effects present another challenge. If the galaxy selection process preferentially includes objects with certain orientations or shapes, it can create artificial alignment patterns. The resulting contamination might be mistaken for gravitational lensing effects. Controlling systematic errors requires extensive testing and validation. Astronomers analyze simulated data where the true answer is known to verify their analysis methods. They also cross-check results using different analysis techniques and telescope systems. The systematic error budget often determines the ultimate accuracy of weak lensing measurements. As telescope technology and analysis methods improve, systematic control becomes increasingly important for achieving precise cosmological constraints. Even perfect measurements with no systematic errors face fundamental statistical limitations. The universe contains only a finite number of galaxies within observable range, limiting the precision of any statistical analysis based on galaxy samples. This fundamental limit is called cosmic variance. It arises because we can observe only one realization of cosmic structure within our observable universe. Other regions of space might have different structure patterns, but we can't observe them to improve our statistics. cosmic variance affects different measurements in different ways. Small-scale structure measurements suffer less from cosmic variance because many independent regions can be observed. Large-scale structure measurements face stronger cosmic variance limits because fewer independent samples exist. The limitation becomes more severe for rare objects and extreme events. Massive galaxy clusters are uncommon, so measuring their properties precisely requires observations covering enormous volumes of space. Even the largest surveys remain limited by small number statistics. Understanding cosmic variance helps astronomers design optimal survey strategies. By balancing survey area against depth, they can maximize scientific return while acknowledging fundamental statistical limitations imposed by the universe's finite observable size. Stars occasionally line up by pure chance in ways that create temporary gravitational lensing effects. These cosmic alignments happen randomly and unpredictably. When they occur, distant background stars suddenly brighten for weeks or months before returning to normal. The phenomenon is called microlensing. Unlike the dramatic rings and arcs created by galaxy clusters, microlensing produces simple brightness variations that look like temporary stellar flare-ups. Only careful analysis reveals their gravitational origin. Microlensing events are extremely rare for any individual star. The probability that a random background star will be lensed by a foreground star in any given year is less than 1 in a million. But our galaxy contains hundreds of billions of stars, making occasional alignments inevitable. Astronomers must monitor millions of stars continuously to catch these rare events. Most monitoring programs focus on dense stellar regions near the galaxy center where stars are packed closely together. Higher stellar density increases the probability of chance alignments. Each microlensing event provides a unique opportunity to study both the lensing star and the background source. The temporary magnification can reveal details about both objects that would otherwise remain undetectable. Every star that acts as a gravitational lens has a characteristic size scale that determines how its lensing effects appear. This scale depends on the star's mass and its distance from Earth. Heavier stars and closer stars create larger lensing effects. Scientists call this scale the Einstein ring radius for microlensing. It represents the angular size that an Einstein ring would have if the background star sat at exactly the right position. For typical stellar masses and distances, this radius measures a few millionths of a degree. These angular scales are far too small to resolve with even the most powerful telescopes. The Einstein ring radius for stellar lensing is thousands of times smaller than telescope resolution limits. This is why stellar lensing shows up as brightness changes rather than visible geometric distortions. The Einstein ring radius sets the timescale for microlensing events. When a lensing star moves across the background star at typical galactic velocities, the brightening effect lasts for several weeks to several months. Understanding these characteristic scales helps astronomers interpret microlensing observations and extract physical information about the lensing systems involved. Microlensing creates distinctive brightness patterns that change predictably over time. These patterns are called light curves, and they contain detailed information about the lensing system geometry, masses, and orbital motions. Simple microlensing by a single star produces a smooth, symmetric light curve. The brightness rises gradually to a maximum, then falls back to normal levels following a precise mathematical shape. The curve's width indicates the lensing timescale. More complex systems produce more complicated light curves with additional features. Binary stars create double-peaked brightness curves. Planetary systems add sharp spikes or dips to the smooth stellar lensing pattern. Each feature reveals specific details about the system. Analyzing these light curves requires sophisticated computer modeling. Astronomers fit theoretical models to observed brightness patterns to determine the best fitting system parameters. The process can reveal stellar masses, distances, and orbital properties. The light curve shape provides information that no other astronomical technique can access. For brief periods during lensing events, astronomers can study stellar systems in extraordinary detail despite their enormous distances. Planets orbiting lensing stars create their own small gravitational effects that modify the main stellar lensing pattern. These planetary signatures appear as brief additional brightness changes lasting hours to days during the main lensing event. The planetary signal depends on where the planet sits relative to the main lensing geometry. If the planet enhances the lensing effect, it creates a sharp brightness spike. If it interferes with the main lens, it produces a brief dimming period instead. These planetary signatures are extremely brief compared to the overall lensing event. While the star creates brightness changes lasting weeks, the planetary effects last only a small fraction of the total event duration. Detecting them requires continuous monitoring with precise photometry. The strength of the planetary signal depends on the planet's mass and its distance from the host star. More massive planets create stronger signatures. Planets at intermediate distances from their stars produce the most easily detectable effects. Microlensing can detect planets across a wide range of masses and orbital distances. The technique is sensitive to Earth-mass planets and can find objects in the outer regions of planetary systems where other detection methods fail. Some microlensing events produce much more dramatic brightness increases than the typical factor of 2 or 3 magnification. When source stars pass very close to the lensing geometry's most sensitive regions, they experience extreme magnification that can boost their brightness by factors of hundreds. These high magnification events occur when the source star crosses what astronomers call caustic curves. These are regions in space where gravitational focusing becomes extremely strong, similar to the caustic patterns that strong galaxy lenses create. Caustic crossings produce rapid brightness changes that can happen over timescales of hours rather than the weeks typical of normal microlensing. The source star's brightness can jump dramatically as it enters a caustic region and drop just as quickly when it exits. High magnification events are particularly valuable for planet detection. The extreme magnification makes planetary signals much easier to detect and measure precisely. Many of the best microlensing planet discoveries come from high magnification events. The caustic crossing phenomenon also provides detailed information about the source star itself. The rapid brightness variations reveal information about the source star's surface structure and properties that would be impossible to obtain otherwise. Many microlensing events involve more complicated lens systems than single isolated stars. When 2 stars orbit each other, or when a star has a planetary companion, the combined gravitational effects create much more complex lensing patterns. Binary star systems produce characteristic double-peaked light curves with specific spacing and relative heights. The pattern depends on the binary star masses, their separation distance, and the viewing geometry. Each combination produces a unique light curve signature. Star-planet systems create different patterns depending on the planet's orbital position during the lensing event. If the planet sits close to the lensing geometry, it produces a sharp spike in the light curve. If it's positioned differently, it might create a brief dimming feature instead. These complex lens systems provide much more information than simple single-star events. Astronomers can determine not only the masses involved, but also the orbital parameters and system architecture. The analysis becomes more challenging, but much more rewarding scientifically. Binary lens modeling requires sophisticated computer analysis to match observed light curves with theoretical predictions. The calculations must account for all the gravitational effects from multiple objects moving in complex orbital patterns. Earth's motion around the Sun creates additional complications for long-duration microlensing events. As Earth moves along its orbit, the viewing geometry between the lens source and observer changes gradually. This orbital motion can modify the observed light curve shape. The effect is called parallax, and it provides valuable additional information about microlensing systems. By measuring how the light curve changes due to Earth's motion, astronomers can determine the distance to the lensing star and calculate its mass more precisely. Parallax effects become most noticeable for nearby lensing stars and long-duration events. The change in Earth's position over several months creates measurable modifications to the expected light curve shape based on pure gravitational lensing. Detecting parallax requires extremely precise photometry and careful modeling of Earth's orbital motion effects. The measurements must account for Earth's changing position and velocity throughout the lensing event duration. The parallax information helps break degeneracies in microlensing analysis. Without parallax measurements, multiple combinations of lens mass and distance can produce identical light curves. Parallax provides the additional constraint needed to determine unique system parameters. Individual microlensing events rarely provide enough information to determine lens masses precisely. However, statistical analysis of many events can reveal the typical masses of lensing objects and the overall mass distribution of stars in our galaxy. The approach combines two key observable quantities from each event. The event duration indicates how long the lensing effect lasts. The maximum magnification shows how much the background star brightens at the peak of the event. These two measurements are related to the lens mass and distance through the laws of orbital mechanics and gravitational lensing. Higher mass lenses create longer duration events with higher peak magnifications. Nearby lenses also produce longer events than distant ones. Statistical analysis of hundreds of events reveals the average properties of the lensing population. The technique can determine typical stellar masses, distance distributions, and even detect populations of unusual objects like brown dwarfs or stellar remnants. This statistical approach has confirmed that most microlensing events are caused by ordinary main sequence stars with masses similar to our Sun. The mass distribution matches expectations based on stellar evolution theory and other astronomical observations. Detecting microlensing events requires specialized observing strategies designed to monitor enormous numbers of stars simultaneously. The rarity of lensing events demands both large statistical samples and continuous monitoring over long periods. Most microlensing surveys focus on the galactic bulge region near the center of our galaxy. This direction provides the highest stellar density and the greatest probability of chance alignments between foreground and background stars. The surveys use wide-field telescopes that can image millions of stars in single exposures. Automated systems take photographs repeatedly, typically several times per night, to catch brightness variations as they develop. Computer algorithms analyze the vast data streams to identify candidate microlensing events among the millions of stars being monitored. The algorithms must distinguish genuine lensing events from stellar variability, instrument problems, and other false alarms. Successful microlensing surveys require years of continuous operation to build up sufficient event samples. The technique demands patience and persistence, but provides unique access to stellar populations and planetary systems that can't be studied by other methods. Some microlensing events reveal planets that aren't orbited around any star. These free-floating planets drift through space independently, having been ejected from their original planetary systems or formed in isolation. Free-floating planet events produce distinctive microlensing signatures. They create brief brightening episodes lasting only hours to days, much shorter than stellar lensing events. The short duration reflects the planet's lower masses compared to stars. Detecting these isolated worlds requires extremely sensitive monitoring systems capable of catching very brief brightness variations. Most free-floating planet candidates are found by accident during surveys designed to detect longer stellar lensing events. The discovery of free-floating planets has revealed that planetary ejection is relatively common during the early evolution of planetary systems. Gravitational interactions between planets can fling some worlds out of their original orbits into interstellar space. These discoveries suggest that free-floating planets might be as numerous as stars in our galaxy. If confirmed, this would dramatically increase the total population of planetary objects and raise intriguing questions about alternative environments where life might develop. Galaxies don't float alone in empty space. Each one sits within a much larger invisible structure that extends far beyond the visible stars and gas. These hidden frameworks contain most of the matter in the universe, yet they emit no light whatsoever. Scientists call these invisible structures dark matter halos. The word halo describes their shape. They form roughly spherical shells around galaxies and galaxy clusters. Dark matter refers to their invisible nature. This material doesn't interact with light in any detectable way. The halos are enormous compared to the galaxies they contain. A typical galaxy like our Milky Way measures about 100,000 light-years across, but its dark matter halo extends more than 10 times further, reaching over 1,000,000 light-years from the galaxy center. These invisible structures act like cosmic scaffolding that holds galaxies together. Without dark matter halos, the visible matter in galaxies would fly apart due to their rapid rotation. The extra gravitational force from dark matter keeps everything bound together. Gravitational lensing provides the only direct way to map these invisible halos and reveal their detailed structure throughout space. Astronomers can weigh cosmic objects in two completely different ways. They can count up all the visible stars and gas to calculate how much normal matter is present. They can also use gravitational effects to measure the total mass, including invisible components. When scientists compare these two measurements, they discover a shocking discrepancy. The gravitational mass always exceeds the visible mass by enormous factors. This comparison is called the mass-to-light ratio, and it reveals how much dark matter each cosmic structure contains. Typical galaxies show mass-to-light ratios of about 10 to 1. This means that for every kilogram of visible stars and gas, there are 10 kilograms of invisible dark matter present. Galaxy clusters show even more extreme ratios reaching 50 to 1 or higher. The mass-to-light ratio varies systematically across different types of cosmic structures. Smaller galaxies tend to have higher ratios, indicating they contain proportionally more dark matter. Larger systems have somewhat lower ratios, but still show massive dark matter components. These measurements provide direct evidence that most cosmic matter consists of something completely different from ordinary atoms, stars, and gas. The most dramatic proof of dark matter's existence comes from studying collisions between galaxy clusters. These cosmic crashes reveal that dark matter and normal matter behave completely differently during violent gravitational encounters. The best example is called the Bullet Cluster, two galaxy clusters that collided and passed through each other millions of years ago. X-ray telescopes show hot gas trailing behind the galaxy groups like cosmic exhaust. But gravitational lensing reveals that most of the mass moved ahead with the galaxies themselves. This spatial separation proves that dark matter and normal matter are distinct components with different properties. The hot gas experienced friction during the collision, causing it to lag behind. The dark matter felt no friction and continued moving with the galaxies. The separation occurs because dark matter interacts only through gravity, while normal matter interacts through electromagnetic forces as well. During high-speed collisions, electromagnetic interactions create drag forces that slow down normal matter but leave dark matter unaffected. This cosmic experiment demonstrates that dark matter cannot be composed of ordinary atoms or any other type of matter that interacts electromagnetically. Traditional gravitational lensing produces flat maps showing where mass concentrates across the sky. But the universe has 3 dimensions, and dark matter structures extend both across the sky and deep into space along our line of sight. Scientists have developed techniques to create 3-dimensional maps of dark matter distribution using galaxies at many different distances as probes. This approach is called weak lensing tomography, borrowing the medical term for 3-dimensional imaging. The technique works by dividing background galaxies into groups based on their distances from Earth. Galaxies at different distances experience lensing from different combinations of foreground structures along their light paths. Each distance group provides information about a different depth slice through space. Combining information from multiple distance groups allows astronomers to reconstruct how dark matter is distributed in 3 dimensions. The analysis reveals not just where dark matter concentrates, but also how these concentrations extend through cosmic depth. 3-dimensional dark matter mapping shows that invisible matter forms a complex network of filaments and nodes extending throughout space, creating the universe's largest architectural framework. Dark matter halos aren't uniform blobs with sharp edges. Instead, they have internal structure with density that varies smoothly from center to edge. Scientists have developed mathematical formulas to describe these density patterns precisely. The most successful description is called the Einstein profile, named after the 3 scientists who first proposed it. This formula describes how dark matter density decreases with increasing distance from the halo center following a specific mathematical relationship. According to the Einstein profile, dark matter density is highest at the halo center and decreases steadily toward the edges. The density drops more slowly in the inner regions and more rapidly in the outer parts, creating a characteristic shape that appears universal across different halo masses. The profile has been tested against numerous gravitational lensing observations and computer simulations of cosmic structure formation. It provides an excellent description of dark matter halos ranging from individual galaxies to massive galaxy clusters. This mathematical framework allows astronomers to predict gravitational lensing effects precisely and compare observations with theoretical models of how dark matter structures formed and evolved. Dark matter halos aren't perfectly smooth structures. They contain smaller concentrations of dark matter nested within the main halo like Russian dolls. These substructures formed when smaller dark matter clumps merged to build up larger systems over cosmic time. Scientists call these nested structures subhalos, and they create subtle additional gravitational lensing effects that require sophisticated analysis to detect. Each subhalo adds its own small contribution to the total lensing signal, creating tiny perturbations in otherwise smooth distortion patterns. Detecting subhalos pushes gravitational lensing analysis to its precision limits. The signals are extremely weak, much smaller than the main lensing effects from the host halo. Finding them requires careful comparison between observations and theoretical predictions for perfectly smooth mass distributions. Subhalo detection provides crucial tests of dark matter theories. Different models for dark matter's fundamental nature predict different numbers and properties of subhalos. Comparing predictions with observations helps constrain what dark matter actually is. The technique has revealed that dark matter halos contain rich internal structure with numerous subhalos at many different size scales, confirming theoretical predictions about how cosmic structure formed through hierarchical merging processes. Dark matter doesn't just clump around individual galaxies and clusters. It forms an enormous web-like structure that spans the entire observable universe. This cosmic web consists of dense filaments connected by massive nodes with vast empty regions called voids in between. The cosmic web represents the universe's fundamental architecture, the scaffolding upon which all smaller structures formed. Galaxy clusters sit at the intersections where multiple filaments meet. Individual galaxies form along the filament networks like beads on cosmic strings. Gravitational lensing can map this cosmic web by detecting the subtle lensing effects created by dark matter filaments. The technique requires analyzing millions of background galaxies across enormous areas of sky to reveal the weak signals from these extended structures. Cosmic web mapping shows that most dark matter lies in the filamentary network rather than in dense nodes like galaxy clusters. The filaments contain the majority of cosmic matter, but produce much weaker gravitational effects because they're spread over larger volumes. Understanding the cosmic web's detailed structure provides insights into how the universe evolved from nearly uniform initial conditions to today's complex hierarchy of cosmic structures. The number of galaxy clusters that exist at different mass ranges provides a sensitive test of cosmological theories. Counting clusters as a function of their mass creates what scientists call the cluster mass function, a fundamental measurement for understanding cosmic evolution. Gravitational lensing provides the most accurate method for measuring cluster masses needed to construct this function. Unlike other techniques that measure only visible matter or make assumptions about cluster physics, lensing responds to all gravitational mass regardless of its nature. The cluster mass function shape depends critically on fundamental cosmic parameters like the amount of dark matter, the strength of dark energy, and the rate of cosmic expansion. Different parameter combinations predict different numbers of clusters at each mass range. By comparing observed cluster counts with theoretical predictions, astronomers can constrain these cosmic parameters with high precision. The technique provides independent confirmation of results from other methods like cosmic microwave background analysis and supernovae observations. The cluster mass function serves as a cosmic census that reveals how dark matter assembled into the universe's most massive bound structures over billions of years of cosmic evolution. Gravitational lensing analysis faces a fundamental challenge. Astronomers observe distorted galaxy shapes, but they need to determine the mass distribution that caused those distortions. This requires solving what mathematicians call an inverse problem, working backwards from effects to causes. The reconstruction process uses sophisticated computer algorithms that test millions of possible mass configurations to find which ones best match the observed lensing patterns. Each trial configuration predicts specific galaxy distortion patterns that can be compared with observations. The algorithms must account for numerous complications, including measurement noise, intrinsic galaxy shapes, and incomplete sky coverage. Modern reconstruction techniques use advanced statistical methods to handle these challenges and extract reliable mass maps from noisy data. Successful reconstruction produces detailed maps showing where dark matter concentrates throughout the surveyed regions. These maps reveal cosmic structure details that would be impossible to observe through any other astronomical technique. The reconstruction process transforms millions of tiny galaxy-shaped measurements into comprehensive maps of invisible matter distribution, providing our clearest view of the universe's dark matter skeleton. Not all scientists accept that dark matter exists as a separate type of matter. Some propose that our understanding of gravity itself might be incomplete, requiring modifications to Einstein's general relativity on cosmic scales. These modified gravity theories attempt to explain gravitational lensing effects without invoking invisible matter. Instead, they propose that gravity behaves differently than Einstein predicted when dealing with very weak fields or very large distances. Different modified gravity models make specific predictions about how gravitational lensing should work. These predictions can be tested by comparing them with detailed observations of lensing effects around galaxies and galaxy clusters. So far, modified gravity theories have struggled to explain the full range of gravitational lensing observations. Most models can account for some lensing effects, but fail to reproduce others, particularly the spatial separation seen in colliding galaxy clusters. The ongoing comparison between Darter models and modified gravity theories helps scientists understand whether cosmic structure requires new types of matter or new laws of physics to explain gravitational lensing phenomena. Gravitational lensing reveals where dark matter is located throughout space, but it cannot determine what dark matter actually is made of. Answering that question requires completely different experiments conducted in underground laboratories on Earth. These underground detectors search for direct interactions between dark matter particles and ordinary matter. The experiments use extremely sensitive instruments housed deep underground to shield them from cosmic rays and other sources of background interference. Combining results from cosmic lensing observations with underground detection experiments provides complementary approaches to understanding dark matter's fundamental nature. Lensing reveals dark matter's gravitational effects, while direct detection searches for other types of interactions. The connection works both ways. Cosmic observations constrain the properties that dark matter particles must have, while laboratory experiments test whether particles with those properties actually exist and can be detected. This combination of astronomical observation and laboratory experiment represents one of the most comprehensive approaches in modern physics for solving one of the universe's greatest mysteries. Light from the same distant object can arrive at Earth at completely different times. This happens when gravitational lensing splits the light into multiple paths that follow different routes through curved spacetime around massive objects. Each light path experiences different gravitational conditions during its journey. Some routes pass closer to the lensing mass where gravity is stronger. Others take longer detours around the gravitational field. These different conditions create measurable time delays between the arriving light signals. Scientists describe these delays using something called the Fermat potential. This concept combines two effects that slow down light: the extra distance of curved paths and the gravitational time dilation near massive objects. Both effects contribute to the total delay time. The time delays depend precisely on the masses involved and the geometry of the lensing system. Heavier lenses create stronger delays. Different path geometries produce characteristic delay patterns that can be calculated theoretically and measured observationally. These gravitational time differences transform lensing systems into precision cosmic clocks that measure fundamental properties of space, time, and cosmic expansion. Astronomers have discovered a remarkable way to measure cosmic distances using the time delays in gravitational lensing systems. When a distant object changes brightness, each lensed image shows the same brightness variation, but at different times separated by the light travel delay. This technique works best with objects that vary unpredictably over time: quasars, extremely bright galactic centers powered by supermassive black holes, provide ideal targets because they flicker randomly due to chaotic processes near the black hole. Scientists monitor all the lensed images simultaneously for months or years. When the background quasar brightens or dims, they see the same pattern repeat in each image with characteristic time delays. Measuring these delays precisely requires continuous observations over extended periods. The time delay measurements provide direct distance information that doesn't depend on other astronomical techniques. The delays reveal the absolute size scale of the lensing system and the distances to both the lens and the background source. This approach creates an independent cosmic distance ladder that can measure expansion rates and cosmic parameters without relying on traditional distance measurement methods. Quasars don't shine with steady brightness like normal stars. They flicker unpredictably as matter spirals into their central black holes. These chaotic brightness variations provide the signals needed for gravitational lensing time delay measurements. The flickering happens because material falling towards supermassive black holes doesn't flow smoothly. Turbulence, magnetic fields, and gravitational instabilities create constantly changing conditions near the black hole. These changes alter how much light the quasar emits from day to day. Measuring time delays requires tracking these brightness variations continuously over periods of months to years. Astronomers must observe lensing systems regularly with high-precision photometry to catch every brightness change as it propagates through the different lensed images. The observational programs use networks of telescopes around the world to maintain continuous coverage. Automated systems monitor dozens of lensed quasars simultaneously, building up the long-term datasets needed for precise time delay measurements. This patient observational approach transforms random quasar flickering into precision tools for measuring cosmic expansion and fundamental physics parameters. Extracting accurate distance measurements from time delay observations requires detailed models of how mass is distributed within the lensing galaxy. Different mass arrangements produce different delay predictions, affecting the final cosmological results. The modeling process must account for every component that contributes significant gravitational effects. This includes the main galaxy's stars, dark matter halo, and any satellite galaxies or other nearby masses. Each component adds its contribution to the total gravitational field. Computer models test thousands of possible mass configurations to find combinations that best match both the observed image positions and the measured time delays. The analysis must simultaneously fit multiple constraints from different types of observations. Uncertainties in the mass models translate directly into uncertainties in the derived cosmological parameters. Small changes in the assumed mass distribution can alter the calculated expansion rate by several percent, enough to affect important cosmological conclusions. Advanced modeling techniques now incorporate additional constraints from stellar dynamics, gravitational lensing analysis, and observations at different wavelengths to reduce these systematic uncertainties. Different methods for measuring the universe's expansion rate are producing conflicting results. This disagreement has created one of the biggest controversies in modern cosmology, with gravitational lensing time delays playing a central role in the debate. The conflict centers on something called the Hubble constant, which describes how fast the universe is expanding today. Measurements using nearby objects like supernova give one value. Measurements from the cosmic microwave background give a different value that disagrees by about 10%. Gravitational lensing time delays provide a third independent method that generally agrees more closely with the nearby universe measurements. This creates a pattern where local measurements disagree with early universe measurements, suggesting something fundamental about cosmic expansion isn't understood correctly. The disagreement might indicate new physics beyond our current models. Alternatively, it could reflect systematic errors in one or more of the measurement techniques. Resolving this tension requires improving the precision and reliability of all methods involved. This cosmological crisis has sparked intense research efforts to understand whether the universe's expansion history differs from theoretical expectations or whether measurement techniques need refinement. Time delay measurements alone don't directly give distances. They must be combined with information about the lensing system geometry to extract absolute distance scales. This combination creates what astronomers call angular diameter distances that probe cosmic expansion directly. The technique works by comparing two different ways of measuring the same lensing system size. Time delays reveal the physical size scale in light travel time units. Angular measurements from telescope images give the apparent size on the sky in angular units. Combining these measurements yields the ratio between physical size and angular size, which directly determines the distance to the lensing system. This geometric approach doesn't depend on assumptions about object brightness or other properties that affect traditional distance methods. The angular diameter distance measurement provides information about cosmic geometry and the expansion history between the observer and the lens. Different cosmological models predict different relationships between angular diameter distance and redshift. This geometric distance information helps constrain fundamental cosmic parameters, including the amount of dark energy, the universe's curvature, and the equation of state describing dark energy's properties. The gravitational field around lensing galaxies isn't perfectly smooth. Individual stars within the galaxy create their own small gravitational perturbations that add tiny additional time delays to the main lensing effect. These stellar contributions complicate the analysis of time delay measurements. Each star in the lensing galaxy acts like a miniature gravitational lens that slightly perturbs the light paths from background sources. The perturbations are much smaller than the main galaxy lensing effect, but can still influence precision measurements. The stellar perturbations vary randomly as stars move in their orbits around the galaxy's center. This creates time-variable components in the delay measurements that must be separated from the constant delays used for cosmological analysis. Accounting for stellar microlensing effects requires statistical modeling of the entire stellar population within lensing galaxies. The analysis must consider stellar masses, positions, velocities, and how they influence light from different parts of the background source. Modern time delay analysis incorporates these stellar effects into comprehensive models that separate the cosmologically useful constant delays from the variable stellar perturbations. Lensing galaxies don't exist in isolation. They're embedded within larger cosmic structures that create additional gravitational effects. These environmental influences can modify time delay measurements and must be accounted for in precise cosmological analysis. The surrounding large-scale structure includes nearby galaxies, galaxy groups, and the cosmic web filaments that connect different regions of space. Each component contributes small additional gravitational effects that influence light paths and travel times. Environmental effects typically change time delay predictions by a few percent. Small compared to measurement uncertainties in early studies, but significant for modern precision measurements. The corrections depend on detailed knowledge of matter distribution around each lensing system. Accounting for environment effects requires mapping the three-dimensional matter distribution around lensing systems using galaxy surveys and weak lensing analysis. This information gets incorporated into lens models as additional mass components beyond the main lensing galaxy. The environmental corrections help explain some of the scatter in time delay measurements and improve the consistency between different lensing systems when used for cosmological parameter determination. Individual time delay measurements contain various sources of uncertainty that limit their cosmological utility. Combining measurements from many different lensing systems helps reduce these uncertainties and provides more reliable constraints on cosmic expansion. Each lensing system has unique properties that affect its time delay measurement accuracy. Some have cleaner mass distributions that are easier to model precisely. Others suffer from stronger environmental effects or more complex stellar populations. Combining multiple systems averages out these individual variations. Statistical analysis of large samples also helps identify and control systematic errors that might affect individual measurements. Systematic biases that are consistent across many systems become apparent when comparing results from different lenses. Modern time delay cosmology uses samples of dozens of well-measured lensing systems to constrain cosmic parameters. The statistical power of large samples allows detection of systematic effects and provides more robust cosmological conclusions than single-system studies. The statistical approach has revealed that time delay measurements consistently favor certain cosmological parameter ranges, contributing to the ongoing tension between different measurement methods. A fundamental theoretical problem limits how precisely time delays can constrain cosmological parameters. Different mass distributions within lensing systems can produce identical lensing effects while predicting different time delays, creating an inherent ambiguity in the analysis. This limitation is called the mass sheet degeneracy. It occurs because adding a uniform sheet of matter throughout the lensing system changes the predicted time delays without affecting the observed image positions or shapes. The degeneracy makes it impossible to determine the true mass distribution uniquely. Breaking the mass sheet degeneracy requires additional constraints beyond basic lensing observables. These can include stellar dynamics measurements, environmental corrections, or statistical arguments based on theoretical expectations for galaxy properties. The degeneracy affects different lensing systems differently depending on their geometry and mass distribution. Some systems are more susceptible to mass sheet effects, while others provide more reliable cosmological constraints. Understanding and controlling the mass sheet degeneracy represents one of the major challenges in time delay cosmology and limits the ultimate precision achievable with this technique. Time delay measurements provide unique insights into dark energy, the mysterious component driving the universe's accelerating expansion. The technique offers independent constraints on dark energy properties that complement other cosmological probes. Dark energy affects cosmic expansion history, which influences the relationship between time delays and distances in lensing systems. Different dark energy models predict different expansion histories that can be distinguished through precise distance measurements. The time delay technique is particularly sensitive to dark energy properties because it measures absolute distances rather than relative brightness or angular sizes. This makes it less susceptible to systematic errors that affect other cosmological distance methods. Combining time delay results with other dark energy probes like supernovae and cosmic microwave background observations provides comprehensive tests of dark energy models. The combination helps determine whether dark energy has constant or evolving properties. Future large samples of time delay measurements could provide some of the most precise constraints on dark energy properties and help determine whether dark energy requires modifications to Einstein's theory of gravity. Upcoming astronomical surveys will discover thousands of new gravitational lensing systems suitable for time delay measurements. These large samples will transform time delay cosmology from a specialized technique into a major cosmological probe. Next-generation telescopes will provide the continuous monitoring capabilities needed for precise time delay measurements on unprecedented scales. Automated survey systems will track brightness variations in hundreds of lens quasars simultaneously. The combination of larger samples and improved measurement precision will reduce statistical uncertainties while providing better control of systematic effects. Large samples enable new statistical techniques that improve reliability and accuracy of cosmological parameter determination. Future time delay surveys may help resolve the current tension in cosmic expansion rate measurements by providing independent checks with improved precision. The technique offers unique systematic error properties that complement other cosmological methods. The next decade of time delay cosmology could establish this technique as one of the most important tools for understanding dark energy, cosmic expansion, and fundamental physics on cosmic scales. The universe started nearly smooth and featureless. Today it contains enormous structures like galaxy clusters connected by vast filaments of dark matter. Gravitational lensing provides the only way to trace how this cosmic architecture evolved over billions of years. The technique works by comparing dark matter maps from different cosmic epochs. Lensing systems at various distances show snapshots of structure formation at different times in cosmic history. Nearby systems reveal current structure. Distant systems show how things looked when the universe was younger. Scientists call this approach structure formation studies, and it tests our fundamental theories about how the universe evolved. Computer simulations predict specific patterns for how cosmic structure should have grown over time. Lensing observations can confirm or challenge these predictions. The measurements reveal that structure formation happened more slowly in regions dominated by dark energy. As dark energy became more influential over cosmic time, it began suppressing the growth of cosmic structures by accelerating the universe's expansion. This technique transforms gravitational lenses into cosmic archaeologists that reveal the universe's construction history spanning most of cosmic time. Neutrinos are among the most abundant particles in the universe, yet they barely interact with anything else. These ghostly particles have tiny but non-zero masses that affect how cosmic structures grow over billions of years. Gravitational lensing can detect these subtle effects. Massive neutrinos move at high speeds even after the universe cooled down from its early hot phase. This motion prevents them from clumping together on small scales the way dark matter does. The result is that neutrino mass suppresses the growth of cosmic structure below certain size scales. The suppression effect becomes visible in weak lensing measurements that map cosmic structure across different scales. Regions smaller than about 10 million light-years show reduced structure growth when neutrinos have significant mass. Larger regions remain unaffected. By measuring how much structure suppression occurs at small scales, astronomers can calculate the total mass of all neutrino types combined. This provides the most sensitive method available for weighing these elusive particles. Current lensing surveys have established upper limits on neutrino mass that complement laboratory experiments and help constrain fundamental particle physics beyond what earthbound detectors can achieve. Einstein's general relativity might not be the complete story of how gravity works on cosmic scales. Some scientists propose modifications to gravity theory that could explain cosmic acceleration without requiring mysterious dark energy. Gravitational lensing provides crucial tests of these alternative ideas. Modified gravity theories predict that gravitational lensing effects should differ from Einstein's predictions in specific, measurable ways. Some theories change how light bends around massive objects. Others alter how matter clumps together to form cosmic structures. The differences between standard and modified gravity become most apparent on very large scales where the proposed modifications are designed to take effect. Galaxy cluster lensing and cosmic shear measurements probe exactly these scales where alternative theories make distinct predictions. Testing modified gravity requires extremely precise measurements that can distinguish between competing theoretical predictions. The differences are often subtle, requiring careful analysis of systematic errors and statistical uncertainties. So far, gravitational lensing observations strongly favor Einstein's original theory over proposed alternatives, but the tests continue becoming more sensitive as data quality improves. The universe began with tiny density variations that eventually grew into today's cosmic structures. These initial fluctuations weren't perfectly random. They contain subtle patterns that reflect the physics of the universe's first moments. Gravitational lensing can detect these primordial signatures. The initial density patterns were mostly Gaussian, meaning they followed the simple statistical distributions found in many natural phenomena. But some theories of cosmic inflation predict small deviations from perfect Gaussian statistics in these early fluctuations. These deviations are called primordial non-Gaussianity, and they would leave distinctive signatures in how cosmic structures are arranged today. Different inflation theories predict different amounts and types of non-Gaussian patterns in the primordial fluctuations. Weak lensing surveys measure the statistical properties of cosmic structure on enormous scales that preserve information about initial conditions. The analysis looks for subtle correlations in structure patterns that would indicate non-Gaussian initial fluctuations. Detecting primordial non-Gaussianity would provide direct information about the physics of cosmic inflation and help distinguish between different theories about what happened in the universe's first fraction of a second. A revolutionary space telescope called Euclid is preparing to map cosmic structure with unprecedented precision. This European Space Agency mission will observe over 1 billion galaxies to create the most detailed dark matter maps ever attempted. Euclid operates from space to avoid atmospheric distortions that limit ground-based telescopes. The stable space environment allows extremely precise measurements of galaxy shapes needed for weak lensing analysis. The mission will survey about 1/3 of the entire sky. The telescope combines visible light imaging with near-infrared spectroscopy to measure both galaxy shapes and distances simultaneously. This dual capability provides the three-dimensional information needed for cosmic shear tomography across cosmic time. The mission's 6-year survey will generate data on cosmic structure formation, dark energy properties, and fundamental physics that will keep scientists busy for decades. The statistical power of billions of galaxy measurements will enable tests of cosmological theories with unprecedented precision. Euclid represents the next generation of space-based cosmology missions that will transform our understanding of dark matter, dark energy, and the universe's fundamental properties. The Vera Rubin Observatory houses the largest digital camera ever constructed for astronomy. This ground-based facility will repeatedly photograph the entire southern sky every few nights, creating an unprecedented dataset for time-variable astronomical phenomena including gravitational lensing. The observatory's survey is called the Legacy Survey of Space and Time, and it will operate for 10 years starting in the mid-2020s. Each night, the telescope will capture images of millions of galaxies and monitor their brightness variations with extraordinary precision. This continuous monitoring capability will revolutionize microlensing studies by detecting thousands of new planetary systems and free-floating planets. The survey will also track brightness variations in multiply imaged quasars for time delay cosmology studies. The massive data volume will require new analysis techniques and computational resources. Machine learning algorithms will automatically identify interesting events among the billions of objects being monitored continuously. The survey will provide the largest samples of gravitational lensing phenomena ever assembled, enabling statistical studies that were impossible with smaller datasets from previous generations of telescopes. Modern astronomical surveys generate data faster than human astronomers can analyze it manually. Machine learning algorithms now play essential roles in finding gravitational lenses and extracting scientific information from lensing observations. Computer algorithms can scan millions of galaxy images in minutes to identify potential lensing systems that would take human experts months to find. The algorithms are trained using known examples to recognize the characteristic patterns that indicate gravitational lensing. Advanced neural networks can also perform complex analysis tasks like measuring galaxy shapes for weak lensing studies or modeling mass distributions in strong lensing systems. These automated techniques provide consistent, objective measurements free from human bias. Machine learning approaches are becoming sophisticated enough to discover new types of lensing phenomena that human astronomers might overlook. The algorithms can identify subtle patterns in large datasets that would be impossible to detect through traditional analysis methods. The combination of vast astronomical datasets with powerful artificial intelligence tools is accelerating the pace of gravitational lensing discoveries and enabling new types of scientific investigations. Gravitational lensing traditionally uses light waves to study cosmic structure, but scientists are now combining optical observations with gravitational wave detections to create more comprehensive pictures of the universe. Gravitational waves are ripples in spacetime itself, produced by accelerating massive objects like merging black holes or neutron stars. These waves carry information about cosmic events that can't be obtained through light alone. When gravitational waves from distant mergers pass through cosmic structures, they experience weak lensing effects similar to light waves. The wave amplification and distortion patterns reveal information about dark matter distribution along the wave propagation path. Combining gravitational wave lensing with traditional electromagnetic lensing provides independent confirmation of cosmic structure measurements. The two types of waves interact with matter differently, offering complementary probes of the same cosmic regions. This multi-messenger approach to cosmology represents a fundamental expansion of observational astronomy beyond the electromagnetic spectrum into entirely new types of cosmic signals. Current cosmological measurements determine fundamental cosmic parameters like dark energy density and cosmic expansion rate to accuracies of several percent. The next generation of experiments aims to achieve percent-level precision that will test our theories at unprecedented levels. These Stage 4 cosmology experiments combine multiple observational approaches, including gravitational lensing, cosmic microwave background analysis, and galaxy clustering studies. The combination provides cross-checks and reduces systematic uncertainties that limit individual methods. Percent-level precision will enable tests of Einstein's theory of gravity on cosmic scales and searches for new physics beyond the standard cosmological model. Small deviations from theoretical predictions could reveal fundamental discoveries about the nature of space, time, and matter. Achieving this precision requires controlling systematic errors at levels that challenge current measurement capabilities. Every aspect of data collection, analysis, and modeling must be refined to eliminate sources of bias and uncertainty. The scientific payoff from percent-level cosmological measurements could include discoveries about dark energy's nature, tests of alternative gravity theories, and constraints on physics beyond the standard model of particle physics. Even perfect gravitational lensing measurements face fundamental limitations that constrain how precisely we can measure cosmic properties. Understanding these limits helps define the ultimate potential of lensing techniques for advancing our knowledge of the universe. Cosmic variance represents one fundamental limit. We can observe only one realization of cosmic structure within our observable universe. This limits the statistical precision achievable even with perfect measurements of every available cosmic structure. Quantum mechanics imposes another type of limit through the fundamental uncertainty in measuring particle positions and velocities. These quantum effects become relevant for extremely precise measurements of cosmic structure on the smallest accessible scales. The finite speed of light creates observational limits by restricting how much of the universe we can observe and how far back in cosmic time our measurements can reach. Some cosmic phenomena occurred before light could travel to our location. Despite these fundamental limits, gravitational lensing continues, pushing toward higher precision and new discoveries. The technique has evolved from an exotic theoretical prediction to one of astronomy's most powerful tools for understanding the cosmos's deepest mysteries.